Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 5, Part 5. This is part of the second lesson of Unit 2 on forces and energy, and it's a continuation on this section on forces Part 2. And we've completed the mandatory part of this. This is an optional part. This involves some trigonometry and Pythagorean theorem, and you're not responsible for any of this. But this is if you are interested in how to deal with forces that are not exactly horizontal and not exactly vertical. That is, they're somewhat at an angle, they're somewhat diagonal. How do you deal with them? And the answer is we do what we resolve the diagonal vector into two new force vectors. Okay, what does that mean? That means that if you have some vector that's pointing at an angle, say here, say that's the force vector, it's not exactly horizontal, it's not exactly vertical, however, it is sitting above the horizon by some angle. And we use the Greek letter theta, the lowercase theta, to represent angles. And if we imagine that our force that we're interested in is the hypotenuse of a right triangle. Those of you who remember right triangles, right triangle has a right angle in it, and there are two shorter sides on that right triangle and one long side. That's called the hypotenuse, and the hypotenuse is the one we're going to start with. We're going to assume that our diagonal vector is the hypotenuse of this right triangle, and we're going to try to figure out what is the length of the horizontal vector and the length of the vertical vector that would complete this right triangle. And as it turns out, if we consider the horizontal one, we call that force sub F, and these are all vectors, so the symbol for vector is an arrow. We don't usually draw it in this class, but I'm going to draw it in here just to be complete. And the vertical component is called F sub y, and that's also a vector. Well, it turns out that if you take a diagonal vector and solve for what the horizontal and vertical vectors are that would complete that right triangle, the sum of the horizontal and the vertical vectors would give you the original force vector that's at an angle. Remember, if you have a vector, let's say that's the horizontal one, and then you do a head to tail to the next vector, the vertical vector, you would get something like that. Well, how do you know what the sum is? The sum is wherever you start and wherever you end, and you just make a new vector there, and lo and behold, we get the force vector that we started with. So if you're dealing with vectors and it's diagonal, you can turn it into the sum of two vectors that are very easy to deal with, a horizontal vector and a vertical vector. And then you can do all your math for just the horizontal vectors and then do all your math for just the vertical vectors separately, making your life a lot easier. Okay, so I'm going to erase a lot of this. And so the question is, how do you determine the length of these component vectors? That's what we call the x and the y vector that we get from resolving the original force vector into its pieces. The pieces are called component vectors, an x component and a y component. You can think of them as a horizontal component and a vertical component. And the horizontal component will be pointing in the general direction of the original vector. So if I had a force vector this way, the horizontal component in this case would be backwards. It would be pointing to the left. The vertical one would still be pointing up. If I had a force vector pointing down like this and we wanted the components, we would make a right triangle, and you'll notice the vertical vector is pointing down and the horizontal vector is pointing to the right. So you can get all kinds of combinations depending on the angle of your original force vector. All right, so let's keep going. We'll look down here. Now, how do you get these component vectors? Well, you get them with a fairly simple pair of equations. The x component vector, the horizontal one, is just equal to the length of the original vector times the cosine of the angle. Okay, which angle? It is always the angle with the horizon being this line here. If we have an angle, if we're looking at the bottom one, the horizon would be here. And we always start the angle on the right side, and we essentially curl the angle up until we hit the force vector that we're interested in. Now you'll notice in the bottom example, your tendency is to pick this angle, and you can get the answer from doing that. The more correct way is to start from the right side and curl it around until you get this vector. But I'm going to tell you, either way, you'll get the correct answer when you do the cosine and sine functions in these two formulas. Okay, you might be wondering, what is a cosine? What is a sine? These are functions that your calculator will do. You have to use your angle. Typically, we measure angles in degrees. So you might have something like 30 degrees, and that's the symbol for degrees, a tiny little circle that's superscripted, and that you'd say, oh, my angle is 30 degrees. And you have to make sure your calculator is in degrees mode. So most calculators can work with angles that are in degrees, but they can also work with a different version of units of angle called radians, and there's even a third version in a lot of calculators. So you always want to make sure that if you're measuring your angle in degrees, you use the degrees mode on your calculator. And then you just hit either the sine button or the cosine button after you've typed in that degree amount of degrees that the angle is. Some calculators switch the order. Be sure which way your calculator works. Okay, so what you would do is you would have your force vector, and then you would type in your calculator the angle, find the sine of the angle, and multiply it by the length of the original force vector, the magnitude, the size, the number of newtons. That's the magnitude. We're not going to worry about the direction of F because that angle will take care of the direction. And then you multiply the sine of the angle times the force, and you'll get the magnitude of the vertical one. And if you multiply it by the cosine instead, you'll get the magnitude of the horizontal vector. So now we've turned this vector here into two easier to use vectors, a vertical and a horizontal, and then we just forget about the diagonal one for now. Now for this bottom example where officially the angle is this angle, I'm going to tell you there's a much easier way to do it than to draw that and try to figure out that angle. Just create a right triangle from your original vector, just like you did before, and do the same calculations with this angle. The angle on the inside, use this theta, not this theta. It's a different number. It will give you almost the same answers, except sometimes the positive and negative signs will be switched. So what I strongly recommend you do is anytime you get a force vector, whether it's pointing down like that or up like that, or up this way or down this way, just make a right triangle where the force vector is the hypotenuse of a right triangle. Draw the right triangle. Forget about finding the official angle that might be on the outside of the triangle. Just find the angle on the inside. Do the same calculations, cosine times force to get the x component, sine times force to get the y component. And then after you're done, ask yourself, okay, is this force pointing up? Okay, yes, it is. It's positive. Is this one pointing to the right? No, it's not. It's pointing to the left. Okay, that one's negative. So then you just assign your positive and negative, just like we've been doing for all the other force calculations in this lesson. You do your calculations and then you assign a positive and negative sign based on the direction that you know that force is in. And this will save you a lot of trouble with figuring out whether I need to go into the angle on the outside. Just use the angle on the inside of the triangle. It'll make it a lot easier for you. Now, how do you go backwards? What if you have component vectors and you need the magnitude of the original vector? Well, we use Pythagorean theorem, which says that if A and B are the short sides of a right triangle, those are called the legs of a right triangle, and C is the long side of the right triangle, the long side is called the hypotenuse, okay, that the length of these, or the magnitude, when you're doing forces, it would be the magnitude of the forces, in other words, how many newtons everything is, it would be A squared plus B squared is going to equal C squared. Well, when you're solving for C, that if you take the square root of both sides, you see that it becomes this formula. C equals the square root of A squared plus B squared. Now, technically, if you're going to take the square root of both sides, at least one of those has to say plus or minus, but the fact is, these are all positive values for now. We'll worry about assigning positive and negatives later. And for C, it's always going to be positive because it's at an angle and we're not going to worry about direction. All right. If you were to solve for A, you use this version. If you're going to solve for B, this version. But typically, you'd be given an X component vector length and a Y component vector length and asked to calculate the combination of these two, what we refer to as the resultant vector, the one that would resolve into an X and Y component. When you go backwards, we call that solving for the resultant vector, or just simply adding the vector. So when you add the vector f sub x, in other words, the horizontal component, to the vertical component, you end up with a new vector that starts from where you started and ends where you ended, and that is the resultant vector. So when you're starting from a diagonal and creating X and Y, we call those resolving the force into the component vectors. And then when we're going from the component vectors to the force, we call that determining the resultant vector. We're simply just adding the vectors, because in vector language, when you add force vector F sub x with force vector F sub y, you get the original force vector. And in terms of Pythagorean theorem, it's just the length of the x vector squared, in other words, the size of how big the force is in the horizontal direction squared, plus how big the force is in the y direction, the vertical direction, squared. You'll get the size of the resultant vector squared. And then if you want the size of the actual resultant vector, this number here, you have to take a square root of that sum that you just did. And now you have the size of that vector. It does not tell you the angle of that vector, and we don't cover that in this course. I will quickly tell you that to get that angle, if you know the length of the vertical force and the length of the horizontal force, this angle can be solved with a trigonometry expression that we haven't talked about called the arctangent, also known as the inverse tangent, which is written like this. And you would take it of a ratio, and the ratio is the ratio of the vertical over the horizontal forces. You take a ratio of that, and once you take a ratio, you use your calculator. It's going to be labeled either tangent to the -1 or arctangent. They mean the same. They mean the inverse tangent function. and that will give you that angle for solving it. But again, this is way beyond the scope of this course. Now, the next page in this area is almost going backwards. It's for people that want to be reminded of what is a sine, what is a cosine, what is a tangent. So here's just a refresher on right angle trigonometry, where the smaller sides of the right triangle are called the legs, and the longer side is called the hypotenuse. But if you're interested in a particular angle within the right triangle, obviously one of those angles is a right angle. So we're not talking about that angle. We're talking about one of the other angles, either this angle or this angle. So if we're interested in this angle, we'll call that one theta. The side opposite of theta is just called the opposite side. And the side next to theta is called the adjacent side. So those are pretty basic names that are always relative to whichever angle you're talking about. If I was to look at this angle here, in this case, this side would be the opposite to this angle, and this side would be the adjacent. So adjacent and opposite are always relative to the angle you're interested in, and that's actually drawn right here. You'll see I switched which angle we're interested in, and you see this is the opposite and this is the adjacent. And the bottom is just to show you that you can switch the triangles around. It's still whatever side is opposite the angle of interest is called the opposite, and the side that's alongside of the angle is the adjacent. And sometimes right triangles can even be drawn where the right angle is up at the top. It almost is used to fool you. It doesn't look like your typical right triangle until you rotate it around. But again, the angle here is the angle of interest, so the side opposite is the opposite, and the side adjacent is the adjacent. Just make sure you don't write it as the hypotenuse, because the hypotenuse is the longest side. That's never an adjacent or opposite. It's always a hypotenuse, and the other two sides are either adjacent or opposite, depending on which angle you are interested in. Okay, now, once you have labeled which angle you're interested in, and you've labeled the sides as opposite, adjacent, and hypotenuse, now you can actually identify the values for sine and cosine of the angle you selected. The angle you selected, and I've redrawn the triangles down here on both sides. The angle you selected, and I've used the same angle, I just flipped the triangle opposite each other. If you take a ratio of the length of the opposite side over the length of the hypotenuse, remember the hypotenuse is always the longest side. If you take that ratio, that is called the sine of the angle. If you take the ratio of the adjacent side to the hypotenuse, that is called the sine of the angle. And if you skip the hypotenuse altogether and you take the ratio of the opposite side to the adjacent side, that is called the tangent of the angle. And if you were to look at the other angle, you're now going to switch opposite and adjacent, so all of these will be different ratios. But these are all ratios of lengths that you can get from a calculator by typing in the angle and hitting the sine button, the cosine button, or the tangent button, depending on which ratio you're interested in. Now, I know that's a lot of information if you've never seen it before, so there's a famous mnemonic that's used that's called SOHCAHTOA. SOHCAHTOA. And that's how you say it. I wrote a little pronunciation guide in parentheses. SOHCAHTOA, SOH, the sine is the opposite over hypotenuse. Ka, the cosine, is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. SOHCAHTOA. Each one of those syllables is defining one of the three ratios. Of course, if you have a calculator and you know the angle, you can instantly get the value of the ratio, not the individual sides, the ratio from just plugging into the calculator sine of theta, cosine of theta, tangent of theta. All right, so let's take a look at how to use these in actual problems. So this is continuing the advanced section. You're not responsible for it. These are practice problems to get the components of vectors. In other words, the magnitudes, the sizes of the horizontal and vertical components of a vector that would add up. If you added that vertical and horizontal, those components together, you would get the original vector. All right, so the x component, as I said before, is the original magnitude of the original vector times the cosine of the angle, and that gives you the component in the x direction. The y component, which is the component in the y direction, the vertical direction, is the magnitude of the original vector times the sine of the angle. All right, so the problem says to sketch the original force vector, I mean, just do the best you can, and convert the following vectors to x and y components. Don't forget signs. All right, so you can either select the correct theta for each angle, the correct angle using the strict rules, or probably better to just use the angle within the right triangle and then assign positive and negative directions to your vectors after you calculate it. Now I'll show you what I mean. All right, so it says you have a 25 Newton magnitude vector at a 30-degree angle above the x-axis. And in some problems, they would say above the horizon. So let's draw what that should look like. So if I draw just a horizon, a horizontal line, an x-axis, and then we ask ourselves, what does this 20 Newton vector look like? I'll change colors here. And you would just pick a starting point and make a vector that has a 30-degree angle above that. So keep in mind, if I was to go straight up, that would be a 90-degree angle. So we want about a third of that. So a 30-degree angle would look something like that. And that's our vector. Just label it 20 newtons. That's our force vector. That's our original vector that we want to make components of. And our components are going to look like the rest of the right triangle. So if I make a line here and make a line here, we complete our right triangle, and then we give it arrows. Since our original arrow is in this direction, that would be the sum of a horizontal arrow pointing to the right and a vertical arrow pointing up. So that's our y component, and this is our x component that we want to determine. And we know that our x component is equal to our original vector times the cosine of theta, and this is our theta. This is our 30-degree angle here. And when you're doing this with your calculator, make sure your calculator is in what's called degrees mode, not rad mode, which is short for radians. Make sure your calculator says degrees, or it defaults to degrees. Otherwise, you'll get the wrong answer. There's a quick way to check if you're in the right mode. Take sine of 30 degrees, and you should get exactly 1/2, 0.5. If you get that, you're in degrees mode. Okay, so we're going to plug in our original force, which is 25 newtons, and we're going to multiply it by the cosine of 30 degrees, which works out to about 0.866. It goes on infinite number of digits, so let the calculator do the work for you. Don't round the number. So you're going to take 30 cosine. I would do the cosine first on your calculator and then multiply that times 25 newtons, and you get a value of 21.65 newtons. And that is your horizontal component. It's this component. And it's in the positive direction, so we'll assign it a positive sign. And the y component, we just use sine instead of cosine on our calculator. And that would be the original force times sine of 30 degrees. And as I mentioned, sine of 30 degrees is exactly 0.5. So it's 25 newtons times 0.5. In other words, half of that. So half of that is 12.5 newtons. And since it's pointing up, we assign a positive direction to that. And that completes that particular problem. All right, let's look at the next one. I'll do it in a different color so it doesn't blend in with the other answers. Okay, we have an 89 Newton force at a 75 degree angle below the horizon, below the x-axis. So how will we depict this? Well, we have our horizon, our x-axis, and we have a very steep angle, 75 degrees. That's most of a 90 degree angle. So we'll start here and we'll go very steeply downward. Doesn't have to be perfect, and we'll assume that that's 75 degrees. Technically, it's a negative 75 degrees, but we have a choice. We can either use the proper negative 75 degrees, or we can make our life easier and do everything with positive angles and then assign a positive and negative direction to our vectors after we calculate them. All right, so what are the components? Well, if this is the diagonal that represents the hypotenuse of a right triangle, well, here's the rest of the triangle. It's this one, and we'd have this horizontal vector that's pointing to the right. That's going to be in a positive direction. But we also have this vertical vector, which is pointing downward. So that tells us that one's going to be in the negative direction when we've finished calculating it. So let's do the calculations just like we did before. The x component is the original force times the cosine of the angle. Well, that is equal to 89 newtons times the cosine of 75 degrees. You could use negative 75 degrees. Let's use 75 degrees and then we'll assign signs afterwards. We plug this into a calculator, and so you're gonna do the cosine of the 75 degrees first. That'll be easier to do on the calculator. Usually multiply it by 89 newtons, and you will get 23.03 newtons. Now you'll notice the sine of an angle and the cosine of an angle, they have no units. So all of the units are coming from your original force, and so your component force will also have the same units of newtons. All right, and we have to assign a sign. As you can see, the horizontal vector is pointing to the right, so that's a positive 23.03 Newton component vector in the x direction, the horizontal vector. The y vector is calculated the same way, but with the sign. We use the sign. Let's get that a little clearer here. Sine of the angle. So we would type in the sine of the angle first, the sine of 75 degrees, multiply that by 89, and you would get a value of 85.97 newtons. 85.97 newtons. But wait, the vector is pointing downwards, so we have to assign it a negative sign. And that would be our y component. Now, if you had used the minus 75 angle, because this is actually going downwards, you would actually get minus 5.97 directly. So I would still recommend just using the angles within the triangle, only calculating with positive values, get your answer, and then decide, is this pointing up or down? If it's down, it's negative. Is it pointing to the left or right? If it's left, it's negative. And that'll make things easier for you in the long run. Okay. And then the last part of this problem says convert the following x and y components back to a resultant force vector. In other words, we're going backwards now. Now you have the two components, and you are trying to determine what is the value of the original resultant vector these two components came from. All right, so let's just draw that. We have an x component vector that is going in the negative direction. That's to the left. And it has a magnitude of 3.4 newtons pointing left. So I'll just write 3.4 and I'll put the arrow to the left. And then we'll do a head to tail with the y component. Well, the y component is positive, so that means it's going up from that direction. And it's going up with not as high as it is wide, because 2.7 is a little less than 3.4. So I go up, and that represents my 2.7 Newton vertical vector. So if I started here and I ended here, then our resultant vector is the sum of those two vectors. It's a vector that looks like that. And it has some angle here that we don't know just yet. I'll label that angle theta. We'll deal with that later. All right, but we don't know the value of the resultant force vector. So how do we get this? Well, this is a right angle, and we can use Pythagorean theorem. Pythagorean theorem says the sum of the squares of the two sides, the two short sides called the legs, equals the square of the long side called the hypotenuse. In other words, the two short sides squared, I add those together and I'll get the long side squared. Well, that works out to being 2.7 newtons quantity squared, and it doesn't matter which order you do those, plus 3.4 newtons squared will equal my force, the original force, the resultant force, squared in magnitude. This doesn't deal with direction. Well, you multiply this out, take the squares, you sum up the squares, and you're going to get a value of 18.85 newtons squared, because we've squared these values, and that's equal to the magnitude of the force, the resultant vector, squared. That means we have to take a square root to get rid of the squares, and therefore the force magnitude, the resultant force magnitude, is the square root of that number, and using your calculator, you find it has a value of 4.34 newtons approximately. Now you might say, well, wait, is that positive or negative? Well, when it's diagonal, there is no positive and negative really. You just give it that value and you say it has a direction, and the direction is determined by the angle. Okay, it's not directly to the left or directly to the right. It's not directly straight up or straight down, so we can't assign it a plus and minus direction. We have to assign it an actual angle direction. So that means we need to figure out what the angle is, and in the proper method, the angle is this angle. It's always from the horizon counterclockwise until you hit the line of interest, in this case our resultant force vector, but we're just going to figure out this angle first. That's a lot easier. Now, you are certainly not responsible for how to do this, but the way to do this is recognize that the tangent of that angle is equal to the ratio of the opposite side, 2.7 newtons, over the adjacent side, 3.4 newtons. And to get the angle, you have to use a function called the inverse tangent. And this is way beyond the scope of the course. But if you took this ratio, you divided it out, you would get a ratio and remembering that this is actually a negative number, so that's negative. You take a ratio, the ratio of that is that the tangent is negative 0.794, and then you take the inverse tangent, you would find that the angle is in fact approximately 38.45 degrees. And that would tell you the angle that it's going. And then this angle here, which would be the technical official angle, is 180 degrees minus that. So this is way beyond the scope of what you required, but that angle would be 141.55 degrees, which is the angle from the horizon going around. And if you were involved in real geometry, or you were dealing with directional forces that were diagonal, this is how you'd properly describe that force. You would say it has a magnitude of 4.34 newtons at an angle of 141.55 degrees. But again, we would never make you do something like this in this course. So how would you apply these methods to an actual free body diagram problem? Well, here's an example of an advanced free body diagram problem with a diagonal force. And in this problem, you see in the diagram below, a father is pulling a cord, a rope, at an angle of 25 degrees with the horizontal, with the horizon, with the x-axis, however you want to word it. The mass of the sled and the children together is 100 kilograms. The tension in the cord is 120 newtons, and the frictional force is 15 newtons. All right, so there's a lot going on here. We have a father pulling a cord at an angle. And so if we draw that angle 25 degrees above the horizon, that's the horizon. This is 25 degrees. And the tension in this, so this is a force of tension. Really, it's the father applying a force. He's applying a force to the rope, and then the rope is applying a force to the sled. So you can think of it as the tension force or an applied force. It's the same thing, essentially. And we know that this is 120 newtons at this angle here. Now, at the same time, you also know that the sled has a mass, and therefore it has a weight. And we can always calculate weight as m times g. That's easy. The sled is not falling through the snow and the ice, and it's not floating up in the air, accelerating. So we know there's a normal force. However, we don't know the size of the normal force this time. We know that the weight force is in the negative direction. We know the normal force is in the positive direction. But there are other things going on, and I'll explain in a second what I mean by that. All right. You also are told there's a frictional force. Frictional force is between the sled and the snow or ice, and that's pointing in the opposite direction that the sled is moving, and that would be in the negative direction. And the movement of the sled is horizontally, so we can make a little note that it's moving to the right. All right. Now, what you have to realize here is that you can't directly analyze a diagonal force like this tension force. You have to break it up into components. So we have to determine the value of the horizontal component of that tension force and the vertical component of that tension force. We have two components. I'm just going to erase this little thing with the velocity. And now we'll label that as the force Y, force component in the Y direction, force component in the X direction. And we'll just not deal with the diagonal one. We have replaced the diagonal with two component forces. And now all of our forces in our free body diagram are either perfectly vertical, either up or down, or perfectly horizontal, either to the right or to the left. And now we can actually start our analysis. So looking at our XY table, we begin to fill in items. In the X direction, in the X orientation, horizontal orientation, we have up, we have to the right, which is positive, and we have to the left, which is negative. Well, the forces to the right the only force is the X component of the tension force. And that's obviously in a positive direction. And the only force also in the horizontal direction left is pointing to the left, and that is the frictional force to the left. The vertical forces, we have more than our usual weight and normal force. We have three things to deal with now. In the upward direction, that's the positive direction for vertical, we have the Y component of the tension force, which is in the positive direction, but we also have the normal force. Now, the normal force does not have to be as big as it usually is. The normal force is not balancing the weight force by itself, because now there are two forces that are there balancing the weight force. The Y component of the tension and the normal force. But we have this weight force, and all three of these are in the vertical direction, either up or down. So now we add up our forces. We have our horizontal net force is equal to our horizontal component of our tension force pointing to the right, and our friction force, which is pointing to the left. Just make a little note that that's negative. As far as our vertical forces go, we have three components to add up. We have the vertical component of the tension force, which is up, plus the normal force, which is also up. And these are both counteracting the gravity force, which is pointing down. Now, we know that these three forces will add up to zero because the sled is not accelerating up into space and it's not accelerating down towards the center of the earth. But the horizontal force total, we don't know what's happening with this. There, we have to add these up, and if this is not zero, if it's something besides zero, there must be an acceleration, and that net force will be equal to the mass of the sled and the kids, which is 100 kilograms, times that acceleration that we don't know about right now. Okay. We're asked to determine the X and Y components of the applied force, that's the tension force, and to add it to our XY table. We've actually added the names of those forces to the table, so we need to actually do the calculations at this point. All right, just redrawing what we've got. We've got a tension force at an angle of 25 degrees, and we are determining the horizontal component and the vertical component. And the horizontal component is going to be equal to our original tension vector times the cosine of theta, which is 120 newtons, that's our original force, times the cosine of 25 degrees. Plug that into a calculator, and we get that force is 108.757 newtons, and we can see that the horizontal force is pointing to the right. Therefore, that's a positive force. Our vertical component is the tension force times the sine of that angle. Therefore, that's 120 newtons still. That's our original vector. Times the sine of 25 degrees. We plug this into a calculator, and we get that the value is 50.714 newtons. And we can see that it is pointing straight up. So that's also a plus direction vector. So we have our two component vectors now. And now that will make calculating everything else much easier. So we're then asked to calculate the values of the missing forces, the force of gravitation, otherwise known as the weight, and the normal force. Well, the weight force is going to be very easy. That you already know how to do. The gravitational force or weight force is mass times gravity. We have 100 kilograms of mass times our good old G of 9.8 meters per second squared. We multiply these out and we get 980 newtons. Now, normally, if there were no other vertical forces besides the weight force and the normal force, to balance those two out, we would just say, oh, the normal force is the opposite. It's also 980, and we remember the weight force is in the negative direction, and we would say the normal force was positive 980. But we can't do that anymore, because remember, the net force in the vertical direction is the sum of three forces now, not just two. Yes, it still adds up to zero, but now we have the vertical component of the tension force, which is in the positive direction, plus the normal force, which we're interested in calculating in the normal direction, plus the weight force, which we already know is in the negative direction. And now we plug these numbers in. We have 0 equals, and using the number we just calculated for the y component, you see is positive 50.714 newtons. We plug that in, 50.714 newtons. That's one value, and that's a positive value, plus our unknown normal force, plus our negative weight force, 980 newtons. Okay, and we can simplify this equation by just adding up those two numbers, this one and this one. We have a positive 50.714 and a negative 980 newtons. We add those together, we get negative 929.286 newtons, plus our unknown normal force. Well, just moving this to the other side, we get our normal force is equal to positive 929.286 newtons. And does that make sense? Well, we have a weight force of 980. It has to be balanced by something. It's partially balanced by the upward force of the tension of the rope of the father pulling the sled, but it has to be also balanced by the remaining normal force. So these two values must add up to the same value as the weight force, but in the opposite direction. Okay, continuing to the next part of the problem. Part E says, using the formula for the frictional force, solve for the coefficient of friction, mu, between the sled and the snow. Okay, well, we know that our frictional force is equal to mu times our normal force, and we just determined our normal force, and we know our frictional force from the problem. We are told that the frictional force from the problem is 15 newtons. So if we plug these values in, we have 15 newtons. And you'll notice I am leaving out the negative sign. I'll put a reminder here it's there. But as I've stated before, when you do your calculations, when you're just doing a calculation to determine a particular term, leave out the positive and negative signs when you're doing especially multiplications and divisions until the very end. Now, if you're adding up things that add up to be net forces, you absolutely need your positive and negative signs in there. But here we're doing something else. We're determining the mu value from two other forces. And mu is always a positive value, and it's always unitless. And it's unitless because it's the ratio of two other forces. Mu happens to be equal to the frictional force divided by the normal force. You can see that from this equation if I just rearrange it, but we'll leave it the way it is. So our frictional force equals mu times our normal force that we literally just calculated. That's 929.286 newtons. And yes, we know it's in a positive direction, but we're not going to worry about that right now. And if you divide both sides by this 929.286 newtons, the newtons cancel, and on the right side the whole number cancels because it's the same exact number, so we get rid of that. So that means mu is equal to this ratio right here. We plug that into our calculator and we see the ratio is a very small number, 0.0161. You might say, well, wait a minute, that's a really small number. Well, it is a small number, but what does mu represent? Mu represents how slick a surface is between two, the contact is between two surfaces. You've got a sled that's designed to slide easily on ice and snow, and it's on ice and snow. So we would expect the coefficient of friction to be a very low number, close to zero. And in fact, it is close to zero, 0.0161. So that's perfectly acceptable and expected even. All right. What is the acceleration of the sled? Well, the sled is moving in the horizontal direction. So we need to know the net force in the horizontal direction because that's equal to the mass times the acceleration in the horizontal direction. Net force is always equal to the mass times acceleration. We're interested in the horizontal movement, so we're looking at the net force in the horizontal direction. And we know that the horizontal net force is composed of two components. It's composed of the tension force in the x direction, which we know is in the positive direction, and the frictional force, which is fighting it in the negative direction, to the left. We know both of these values. We've calculated them already. The x component is 108.757 newtons, and that's positive, plus a negative 15 newtons for the friction. We know that's a negative value. Now we're adding forces. When we're adding up forces, we keep the positive and negatives in there. When we're determining the forces by multiplying and dividing, this is when we hold off on the positive and negative directions until the end, and we make a decision which way it goes. So we add these two terms together. We have a positive number and a negative number. We add them up, and we get positive 93.757 newtons. This is our net force. It's our net force, and it's in the x direction. Our net force in the y direction is 0, so we don't have to worry about it at all. So now, to get our acceleration is just the net force divided by the mass, and that comes directly from this equation, just rearranging it. You can either use this equation directly and solve for the acceleration, or use the version of it that solves for acceleration directly. Now we just plug these numbers in, positive 93.757 newtons divided by our mass. Remember, mass is always in kilograms, so we're looking for our kilogram value. That's 100 kilograms. We divide this out, and you don't even need a calculator for it, but use a calculator if you're not sure about it. It's 0.93757. I know that's a lot of digits. We don't need all of those. And we're dividing newtons, which is really kilograms meters per second squared, and then we're dividing it by kilograms, so that gets rid of the kilograms, so all we're left are meters per second squared. Do you need to do that? No, you just need to remember that all accelerations are going to be in meters per second squared, and this is a positive acceleration. How do you know? Because they're being pulled to the right, and they're increasing their speed to the right. And if you want, because we've got so many extra digits here, if you rounded this to 0.94, that would be perfectly acceptable rounding for your final answer. And that's it.